Hi, everyone. We'll be starting the webinar shortly in just a few minutes. In the meantime, I'd like your feedback as to how well you can see me, how well you can hear me. Is the audio working? Is the video working? Let me just get a few things sorted out. Can you see my screen right now? All of that. You can hear it and you can see it. Okay, awesome. Thank you for the feedback. So we are going to be starting in like 20 seconds. I'm going to start at 7 a.m. sharp, 7 p.m. sharp. I mean at 12 p.m. Louder. Okay. I think we can start now. Everyone, hello. Today we are going to be talking about neural networks. We are going to be covering just the sort of the basics of neural networks. We will be talking about where we can apply them, where we can use them, and how we can go about creating them a bit more. We will also be going a little bit into the theory of how we actually do that. So if at any time you want to ask any questions about any of the organizational stuff, any of the theory, please feel absolutely free to do so. You can just drop a question in the chat, if I can access the chat, and I will drop some of the contacts of our organization. These are the contacts of our university. So first, we will talk a little bit about us, a little bit about our organization, just a few minutes, and then we will go on to the actual content. So the actual content is going to take about 2 hours. Anyways, a little bit about us. We are a commercial university. So we do two things. We teach people how to use neural networks, how to make neural networks. We do all of that. And we currently have over 15,000 people. We have almost 2,000 people that are actively enrolled in our courses from all over the world. And we offer 15 courses. We have two main courses that we will be offering. In these courses, you don't have to know anything at the start. We will teach you just from scratch. And by the end of that, you will be able to become a junior developer. You will be able to make all kinds of complicated neural networks that we have out there nowadays. So our university is almost 2 years old. All of the content that we've made in our lectures is our own content. So all of it belongs to us. It was made by our team of developers. We have 11 developers that are actively employed that are making all of this content. In our main courses, we might go over topics like regression or classification neural networks. We might go over something like text classification, and that will be just one simple topic, one simple lecture. But we will also have like a whole entire course that focuses much more deeply on that. We have courses that focus on the mathematical aspect of neural networks, that talk about all of the very complicated math that you can use to create your own frameworks. So right away, I want to mention that math isn't a specific requirement. You don't need to know a lot of math, and you don't need a lot of code to use neural networks, because we will be using frameworks, and it's very easy to create neural networks using these frameworks. Like middle schoolers don't experience many problems with this. But if you want to become a senior developer, if you want to know even more, if you want to get more into the nitty-gritty stuff, then we have courses that focus on that. We have courses on the other end, we have courses that can gently introduce you into the topics. So a lot of people that come to our courses, they come from all walks of life. So it's not strictly necessary to know a lot of math. You don't have to know any code at the beginning. But if you are still feeling a little bit uncomfortable for whatever reason, you can always take our courses that will gently glide you into the material. Like we have some introductory courses to Python. Python is the programming language that we will be using to write our neural networks. We have, I believe, some courses. We have one course that deals with the sort of the basics of the theory, just a pure lecture course. Our university, the other thing we also do is we do sort of commercial projects. So we have a few ones that we are very proud of. We made one neural network that is able to, just by looking at a photo of like maybe some skin rash or something, it is able to classify exactly what that skin rash or whatever skin disease it is. It can give advice on how to treat it. It can give advice on just sort of what it is, how to treat it. Right now, we are working to improve the accuracy of that neural network. Right now, it's not quite as accurate as we want it to be, but it's still pretty neat. And we think that once we give it a bigger database to learn from, it will be even more accurate. The other project that we're even more proud of is, it's basically the same thing, but it allows a person to describe their diseases through words, like verbally or by text. So you can say something like, oh, my back hurts. Oh, I have chest pains when I do this and that. I sometimes have some trouble breathing, something like that. And the neural network is able to, provided that it's a sufficiently, like it's a good description, it is able to classify the exact disease with 98% accuracy, which is actually more than what many doctors can say. So this is a trend that we will be seeing quite often. A well-made neural network that has been trained on a good database is able to, it's making less mistakes, it's able to perform its jobs. In the meantime, it will be making less mistakes than actual human experts. So we have a few other projects that we're really proud of. We really have a ton of projects, and talking about all of them will take all day. So I'm just going to mention a few quick ones. We have one where a drone is able to sort of fly on its own, fly inside the interior of some building. It can take photographs, and from those photographs, it can retrieve any kind of useful information. So it knows where it needs to fly. For example, it might know that, okay, if that door over there is not open, then like if it's a closed door, then it can't fly through that. But if it's open, it can retrieve that information and it can sort of plot its own course through the interior of that construction site or that building. It can see a window and it can judge if the window is open, it might try to fly through that. And in the meantime, it will be taking all kinds of photographs of the entire place. And then by analyzing those photographs, it is able to filter and extract the useful information on its own. Like it might say something like, the walls still need to be painted, or the railing was done yesterday. So it can show what kind of progress was made and what still needs to be done. And the other really amazing project, I'm saving the best for the last. We are currently working on a neural computer interface. So typically we interface with the computer using just the mouse and the keyboard. You know, we move the mouse around, we type stuff. We have been able to do this just by attaching some nodes to a person's head and getting them to think really hard. And that moves the computer mouse. Just using the person's brainwaves, the computer is able to type some text in. Right now, this project is in its beginner phases, sort of. But we are hoping to like really complete it, and we think that it will really revolutionize how people use computers in the future. So in this example, the neural network learns what each of the person's thoughts mean. So it reads the brainwaves and it sort of understands what the person wants to do based on those brainwaves. Like if they think really, really hard, like I want this exact text to appear on the screen, that text will appear on the screen. Okay, so enough about us for now. Okay, first of all, actually one more thing I want to mention about us. So we are a university that deals exclusively with artificial intelligence. From top to bottom, all we deal with, everything we work on is in some way, shape, or form related to artificial intelligence. Okay, now enough about us. Let's get on to the actual content. So first, we want to know where we can apply artificial intelligence. And actually, before that, we want to know what artificial intelligence is. How do we define what is artificial intelligence? Well, the very simple answer is that artificial intelligence is anything that performs some kind of intellectual task. So what's an example of an intellectual task? I think it's easier to give an example of a non-intellectual task first. I play a lot of video games. I imagine that many people who are watching this right now play a lot of video games. Video games contain a lot of computer code. There are a lot of algorithms that define how characters move, how projectiles fly if you're playing some shooter game or something like that, how the graphics are generated. Something like 3D graphics that takes an incredible amount of math in and of itself. But in simple terms, a game is just running on a loop. It's just a set of commands. It's a program that runs in an infinite loop. And then if you were to, so it's like checking which conditions are met every time. If you were to press the escape button, for instance, that loop would break and the game would stop playing. But otherwise, it's checking like if this button is pressed, then this character moves forward, or if this button is pressed, then something else happens. You might press another button that brings up the menu, and the menu is another loop that runs in the same sort of fashion, and it's checking if some condition is met, and whatever it does based on that condition is usually another very complicated algorithm, like defining how something or some character is going to fall due to gravity. That takes a lot of math. And there is just an incredible amount of these tiny, or in some cases, very large and complicated algorithms scattered about in this bigger program. So I made a very simple video game once, like a very, very simple video game. And it took 3,000 lines of code. That was as compressed as it could possibly be, and that was including all of the libraries that didn't go into that. If it was made without libraries, it would be much more. So there's just an incredible amount of content in whatever code there is. A more complicated video game will have like millions of lines of code. And it's a wonder that we can not only just create all of that software, but that we have created the hardware which is able to run all of it. But every single step in all of that programming, every single step that the computer does there is predefined. A human at some point or another, or many humans, many different programmers, many different developers, looked at all of this code, they wrote all of this code, and they said, okay, if this condition is met, do this thing. If this condition is met, do this thing. Otherwise, do this thing. So the computer doesn't actually do any of its own original or creative thinking in that. It just does whatever it's told. But let's suppose that we have a more complicated example. Let's say that we want the computer to actually see an image and retrieve some information based off that image. For a very simple example, let's use a cat's dogs classifier. This is kind of like the hello world of machine learning. It's one of those very simple tasks for machine learning. But doing something like that using any sort of hard-coded algorithm is going to be incredibly difficult. In fact, it's going to be impossible. It's going to be possible maybe in theory, but in practice, I think that even in 1,000 years, if we didn't have machine learning, no one would be able to do something like that. Like maybe someone, like some absolute genius, would be able to come up with some algorithm that could do this to some reasonable accuracy, but we want not like 70 or 80% accuracy, we want 100% accuracy. This is just one of those examples of problems that can't be solved using any sort of hard-coded algorithm. Like a cat or dog can be drawn in all kinds of different styles. You can have cats and dogs of different breeds. They can be like in different poses, like either running or lying around or You can have many cats in a single image. It can be a photograph. It can be a Microsoft Paint doodle, anything like that. And the problem is that for some combination of pixels, we want to say that this is a cat. And for some completely different combination of pixels, we want to say that that's a dog. So not possible to do with a hard-coded algorithm. This is just one of those examples. On the more practical end, we have examples like recognizing audio or recognizing the meaning of some text. Whenever you say, okay, Google, so that's something that a neural network interprets. Whenever you want to write a review, if you watched a good movie or a bad movie, you want to write a review. And depending on that review, an AI might try to classify if that was a good review or if that was a bad review. It might try to predict which price you gave it, predicting the stock price. And we have any number of other algorithms like that. Tesla's self-driving cars. So here we have some more examples of where artificial intelligence is used. By the way, folks, if you have any questions throughout the presentation, please feel free to write them in the chat and I will try to answer them as soon as possible. So everything that you see on the screen right now is an example of artificial intelligence. This is the product of some artificial intelligence. It might be surprising, but all of these people that are presented right here, they don't actually exist. All of these faces were generated by a machine. And you can kind of see if you look by column, like if you look like column by column, that these people, they sort of have the same pose, they have the same facial structure, like they're looking at the camera from the same angle. And you can see this for every column. All of these people are the same and all of these people are the same. In fact, these people don't actually exist. They never existed. These faces were generated by a machine. You can actually go online and there is a website that looks something like, the URL is something like thispersondoesn'texist.com. And it can generate a face of a person to you just like on the fly. In this example, we see a neural network editing a photograph. So in the top row, we have the original photograph, and then the people who created this neural network, they like maybe decided to erase the hair over here, and they just sort of doodled on top of that with a pencil. The neural network understands that something that looks like this, where if it's located on the top of the head, then it corresponds to human hair. So it is able to edit the whole photograph and draw the human hair here. So the intellectual task here is that the machine actually knows that if something is located on the top of the head, then it's going to correspond to the hair. And it knows that if it's drawn like this, it's trying to recreate the exact style of the hair. Like we can see that the hair is sort of, it has some red and it has some brown. And it's trying to combine those two colors. It's not just trying to have like one half of the hair be pure red and the other half be pure brown. It knows that, well, some people do that, but more frequently when people dye their hair, they usually have like a blend of colors. So the machine sort of has learned that. And then we have this example, which is my absolute favorite. This is an example from NVIDIA. The left-hand side contains an MS Paint doodle of some landscape. We specify which color explicitly corresponds to which type. Like we can explicitly specify that this brownish color corresponds to some rock. We can say that this bluish color that we see on top corresponds to the sky. Like that part is explicitly stated. But the neural network is able to interpret all of this, and it's able to create a landscape that looks exactly like, or not exactly, but generally like what it sees in the picture. It's able to, like when it sees this green color, it is able to generate some sort of unique terrain. Again, this terrain that we see on the right-hand side, it doesn't exist. And the most amazing thing about this particular neural network is that not only is it able to create all of these terrains, but it knows what sort of, what the terrain, it knows which terrains fit together. Like you probably won't be seeing a lake in the middle of a desert, right? And the neural network knows that. When this waterfall is drawn in the actual demonstration, the entire landscape around it changes. So when we have waterfalls, we have erosion. Millions of years of flowing water causes erosion. And the neural network understands that. So it is able to sort of carve out everything from this whole cliff to sort of give that feeling of the erosion. It's able to draw some plants around it because when we have water, it's more humid. And it sees that like we have reflections coming from the water. And the best part is at no point were any of these correlations actually explicitly explained to the neural network. The neural network has learned all of these correlations on its own just by viewing a lot of data. So we will explain how it does this a little bit more later on in this lecture. And then we see some other examples here. We have image segmentation. That's when a neural network is able to extract what is in an image, like what the contents of an image are and where exactly everything is located. Like it's able to say that the top right corner contains a car and the top left corner contains a person, and so on. Then we have this example here, which is the neural network converting a photograph that was taken using a 360 camera into a 3D model. So this is something that humans can't really do. It's very difficult for humans to visualize this. Then we have this other example from NVIDIA. We have a dash cam that was like footage from a dash cam, just a car driving around, taking some footage that was filmed in the winter, and the neural network converts that whole video to make it look like it was taken in the summer. So people who are wearing winter clothing now wear summer clothing. All of the snow is melted. We have grass growing and everywhere, which is another really amazing example. So NVIDIA, and in fact, most of these neural networks that we see right here are examples of generative models. These are neural networks that generate content on its own, on their own. That isn't the only field where we can apply neural networks. In fact, we can apply neural networks just about everywhere. We'll be talking a little bit more about that as well. We can apply neural networks in just an unbelievable number of places. You can also create something that isn't video, like you can create music, or you can write text. There is a very humorous example online of a neural network that sort of water and something that looked like a pile of ash. There's actually like someone animated the whole thing. It's very humorous to watch because it's not very good. So neural networks, they aren't able to match human creativity in a lot of places. We haven't reached that point yet where we have every single way and perform this wide variety of tasks. Instead, nowadays, we have that can drive cars, for example, won't be able to predict the weather, or won't be able to drive cars. So to recap, artificial intelligence, intellectual tasks, excuse me, some sort of intellectual tasks. Everybody, I'm so sorry, my internet died and I switched over to a new connection. So that's not going to happen again because this connection that I'm using right now is more reliable. Apologies about that. Okay, so to recap, I hope that the internet wasn't out for too long. So to recap everything that we covered, artificial intelligence is able to perform some sort of intellectual task. It's able to think a little bit outside the box. It's able to think a little bit outside this narrow set of instructions that programmers give it explicitly. Right now, we don't have general artificial intelligence, which is able to mimic like actual intelligence, like when we see in the movies, like the Terminator movies, Skynet, or even something simpler like R2D2 from the Star Wars movies, something like that. We don't really have that, but we will have something like that sooner or later. Scientists are absolutely convinced that it's possible. Right now, we have narrow or specific artificial intelligence, which is able to think a little bit outside the box, but it's not able to apply its thinking to all sorts of different tasks that have no sort of correlation between one another. Okay, let's talk a little bit about data science. Neural networks are closely related to data science, and data science is the absolute top profession in the workplace nowadays. So in the United States, data scientists are just the most in-demand profession. And that will continue being the case for a while, like 1 or 2 decades, I think, at the very least. After that, we might have a new, really, really hot topic, like maybe something like genetic engineering. A lot of people are saying that that will be the next big thing. But right now, it's data science. Data science is when we analyze data and we try to find some sort of correlation between all of that data. So we can have huge data sets. We can have data sets of millions and millions of entries containing all sorts of parameters like the age of the person and their marital status and all of that versus the final result. We would want to get something from that data. We would want to, for example, set their insurance price or something like that based on all of these parameters. So data science is separated into 2 parts. We have analytics. This part is mostly done, well, historically it's been done by humans. For example, let's say that one field where this is commonly used is where we might have someone applying for a bank loan, for example, a mortgage. Historically, whenever this happened, so the bank wants to hand out the loan, right? It wants to give the loan to whoever is applying for the loan because the bank knows that it will be paid that loan back plus some percentage on top. But sometimes there are those people that default on their loan for whatever reason. And the bank wants to know who it can trust to sort of pay back that loan and who it doesn't deem as creditworthy. So typically the bank would ask for all sorts of personal information from the applicant, like their age, their marital status, and a bunch of other stuff. So after that, historically, a human data scientist would try to predict all of that information. They would ideally want to make some sort of mathematical function that is going to take in all of those parameters, like the age, the marital status. Probably you'd want to be looking more at something like the credit history and the income. You know, something like marital status is one of those more niche things. And they would try to find all sorts of correlations between that data. Like it stands to reason that people who earn less income probably wouldn't be able to pay off very big loans very easily. So they might be more prone to defaulting on their loan, or people who haven't been employed as much, people who haven't been in the workforce as much or have been unemployed for a very long time. They might not be able to pay back that loan. So these are the no-brainer sort of correlations. But a data scientist might find some more tricky correlations. Like maybe, and I'm just purely making this up as an example, but maybe people who are married are less prone to bankruptcy, or maybe people who have fewer kids are less prone to bankruptcy. Once again, I'm making this up. I have no idea if any of this is true. The data scientist would ideally want to create a mathematical function, some mathematical function like f of x, y, and z equals some sort of addition, multiplication, subtraction, something like that, that is going to take all of those parameters of the marital status, number of kids, income, credit history, number of previous bankruptcies, and whatever else you have, and they would want to perform some strange, weird mathematical computation on that. And that's up to them which mathematical functions they want to use, what they want to actually do with that data. But ideally, they would want that function to give a single result, 0 or 1. So 1 would mean that, yes, this person, we trust them, they're creditworthy, we want to give them that mortgage. And 0 would mean that, no, they're not trustworthy, we want to withhold that mortgage. So this mathematical function would work with numbers. It would only work with numbers. So data like married, yes, no, or employed, yes, no, that would be converted to numerical format. A 0 might mean no, not married or not employed, and a 1 mean employed, married, and so on. Historically, all of this was done by computers. Historically, all of this was done by people. What am I saying? Historically, all of this was done by people, actual human data scientists who would come up with the equation, how they want to process that data, what they want to do with it. But as time went on, more and more of this was done by computers, by machines. This is where machine learning algorithms come into play. And nowadays, this is almost exclusively done by machine learning algorithms. So machine learning algorithms, they existed way back in the middle of the 20th century. They stretch way back to the mid 20th century. So they've been with us for a while. But historically, they haven't been very powerful. Neural networks, specifically. Neural networks are a type of machine learning algorithm. They have been with us from the 1950s. They were actually created because biologists made a sort of interpretation of what they thought the brain looked like, and then mathematicians looked at that and they said, oh, that's neat, let's convert that into digital format, let's see what we can do with it in a mathematical sort of sense. So that's where neural networks come from. But historically, neural networks have been very, very weak. They haven't been able to predict all of this data. So if we were to look at, say, the year 1995, by that time, a lot of classical machine learning algorithms are like k-means clustering or random forests, decision trees, something like that. They would have dominated the whole sphere of machine learning. But as time went on, neural networks would grow more and more within that sphere. So if this representation right here on the screen, maybe it shows the situation as of 1995 with maybe an even bigger portion that looks like this. I don't even have enough room to draw it on the screen, but maybe this part would be the just human data science. If this is what the situation looked like in 1995, then this is what the situation looks like today. Classical machine learning algorithms have just been completely pushed out, almost completely. Neural networks dominate the whole sphere. So first of all, almost all of data science, or rather a huge portion of data science, is being done by machine learning algorithms nowadays. And within the sort of the role of computers within that, neural networks have absolutely exploded in their use. Neural networks nowadays are much more efficient. They are able to give us much better results than any other machine learning algorithm is. The reason why neural networks have become so much better nowadays is because we have a lot of processing power we can use now. We'll also be talking a little bit about this more. Neural networks require a huge amount of processing power. In fact, we barely have the processing power we need to work with them today. But before the previous decade, this was pretty much impossible. Nowadays, neural networks perform better than any of the classical ML algorithms, probably like 80% of the time on some simple task. And classical ML algorithms might win over like 10% of the time. And the other 10% of the time, it's a rough draw, but we will mostly use neural networks anyway because we have all of the frameworks that exist specifically for neural networks. It's just the force of habit, I guess, the force of inertia, you could say. So neural networks are used much more frequently now. Then within this sphere of machine learning that is solely done by neural networks, we have two more categories. So first of all, we have two categories within machine learning. We have simple tasks. Simple tasks are like classifying cats and dogs. Maybe something like predicting which text was written by which author, judging by how many words were used how many times. Some simple sort of algorithm like that, or determining that handwritten digits, for example, that this is the digit 2, and that this is also the digit 2, and that this is a digit 2. Something like that falls into the sphere of simple tasks. But right now, we are seeing more and more of what is called deep learning. We see these deep neural networks. So an example of deep learning is something like recognizing audio, or converting audio into text, or analyzing audio, judging by the sort of the intonation of the voice. Is that person aggressive? Are they scared, or something like that? Another example might be something like, well, self-driving cars, teaching a car how to drive through the road, to what it can do, what it's supposed to do in any given number of situations. Even more examples, so we might have something like taking a photo of some plant and determining based on that photo, is that plant sick or not? And we have just a huge number of more examples. So deep learning algorithms, deep learning problems, they can only be performed by neural networks. We cannot perform them with classical machine learning algorithms. The proportionality between the deep learning tasks and the classical machine learning tasks that we have is also growing nowadays. So we see more and more of deep learning algorithms being used. Let's talk a little bit about some of the advantages and some of the disadvantages that come with neural networks. Is text sentiment analysis more simple or deep learning oriented? That's a very good question. I would say, and this is the tendency with a lot of tasks, it depends on what sort of complexity you want to do that task. You can perform sentiment analysis just by using bag of words, what are called bag of words. You're basically looking at which words were used how many times, and based on how many times each word was used, you would be performing that analysis. That's an example of a simple task. But you can have a deep task which would give much better results, like a deep learning task that is going to actually retrieve the meaning of that word. It might say something like, running and walking are two similar verbs. So a deep neural network might know something like that. When we see image data, so classifying cats and dogs is a simple example. It's an example of a simple task, but a deep learning task might actually look at that image, and it might actually highlight like the cat's face and say, okay, this is the face of the cat, and it might actually compare the face of that cat to the face of some other cat and say that these are two different cats. Like it can perform facial recognition based on that cat. By the way, facial recognition is another example of a deep learning algorithm. So it depends on which level you want to go to, I would say. But that's a very good question. Thank you for asking that. The first advantage of neural networks are able to learn on their own. We will be feeding examples of real tasks to neural networks. Sorry, not real tasks, what am I saying? Like real data to neural networks. If we want to classify cats and dogs, we would show that neural network many, many different examples of cats and dogs, pictures of cats and dogs in all sorts of environments, all sorts of breeds of cats and dogs. And the neural network is going to learn based off those examples on its own. We won't need to sort of babysit it. We won't need to explicitly tell it any sort of information. It will pick out all of these correlations on its own. The, the disadvantage that comes with that is that any neural network requires a huge database to learn from. If you think of an example of a human being, for example, let's compare a neural network to an actual live human being. Let's compare the moment when a neural network is created to the moment that a human is born. If you were to have a newborn child, let's pretend for a moment that you could converse with that child, you can explore, like, exchange information, and you were to ask that child, like say, okay, Billy, these are two trees that you see in the distance. We have a pine tree and an oak tree. Can you tell me which one is which? The child would obviously have no idea. Like, the child was just born, it's never even seen the sun before. It doesn't know the difference between a pine tree and an oak tree. Neural networks are very similar. When they're born, so to speak, they don't know anything, but they are able to learn on their own. A curious child might explore a bit, it might see different oak trees, different pine trees, and learn that there is a difference between those types of trees. A neural network works very similarly, except whereas a human might need something like a few dozen examples before they reliably know the difference between something like this, something simple like this, a neural network is going to need more like tens of thousands of examples or hundreds of thousands, depending on the exact task you want to perform. So the database that will be collected is huge. And databases actually take quite a bit of effort to collect. They take time and they take money to collect. Very often, especially big companies, they have their own departments actually. Big companies, they would often have their own department that is responsible for just collecting a database. And that department might hire freelancers. It can have dozens or potentially like 100 people employed. And even freelancers would usually hire another freelancer to collect a database for them. The other big advantage that comes with neural networks is that they don't require expertise in whatever given field we have. So in other words, we don't need to hold a medical degree in order to create a neural network that is able to classify, that is going to be able to predict or classify diseases. Oftentimes, it is actually going to be able to do this better than actual human experts in the field. So we have right now a neural network that can be more accurate in predicting some diseases, in predicting all kinds of diseases actually, than actual human doctors. It definitely helps to hold a medical degree or have some sort of experience for whichever field you are trying to create a neural network for, but it's not an absolute must. Oftentimes you can get away with just consulting the people who actually work in that profession, who actually work in that field, or something like that. So it's often a lot of the time, like for medical neural networks, you will need to consult actual doctors and have them probably actually evaluate how well the neural network predicts data before pushing it out into its final production stage where it will be used in the market. The other big advantage is that neural networks, well, we talked a little bit about this, they are able to give better data, give better results than actual human experts who have spent their whole lives studying the field. That is the case if the neural network is well made and if it's trained on a large, comprehensive, high quality data set. We see this a lot of the time. One example that comes to mind is one of the people who completed our courses. We have a thesis project, we have a thesis project at the end of our course, our main course, and our student's thesis project was predicting the defects, what kind of defects exist in a metal, just based on, I guess, something like if it sees like some microfractures in that metal, or if you predict like by analyzing it with some other instrument or by a photograph, it would combine all of this data and try to predict classify if there are any defects in that metal. That neural network was accurate to within about 97, 98%. Human experts who spent their whole lives studying metallurgy were only accurate to within about 85%. So humans are prone to error. Neural networks can also sometimes be prone to error. We will also discuss how they're prone to error and how we can overcome that. But a lot of the time, a well-made neural network is going to be less prone to error than humans are. With that said, let's talk a little bit more. So we covered that neural networks, they need big databases to learn from. The other disadvantage is that they require lots and lots of processing power. We haven't been able to harness the full potential of neural networks until quite recently because of this. We simply didn't have the hardware. Nowadays, we have the hardware to get good results, but it remains to be seen. I think that when we have even better hardware in a decade or two, we will get even better results. So in terms of processing power, a CPU isn't going to cut it. We will be training our neural networks. In fact, everyone trains their neural networks on GPUs. As it turns out, the graphical processing unit, it is optimized for performing all of the calculations that neural networks actually require. It can perform them about 50 to 100 times faster than CPUs can. The exact number depends on which hardware you're using, but in my experience, the GPU is about 50 to 100 times faster than a CPU. So if we didn't have a GPU, even with a GPU, it can take like a very high-end neural network that is especially one going to be made by some medium or big company. It can take days and weeks to train. And you can imagine that without the GPU, it would take months, years, potentially even decades to train just one neural network, which is unacceptable. And that also comes in with just a little point about the electricity consumption. When we're training large neural networks, the electricity, like the power consumption, will actually impact the budget a little bit. So the last big disadvantage is that neural networks, they are a sort of black box. They take in some input, they create a very, very complicated, very, very intricate mathematical function, sort of like going back to the analogy with the human data scientist who creates the mathematical function that is going to take in a bunch of inputs and decide whether or not to give a person the mortgage, the loan. Neural networks are going to do the exact same thing. But, well, first of all, they're going to create a much more intricate sort of equation. But the problem is here that they don't really explain why that equation is the way it is. Neural networks, their logic will be really abstract. They will find some weird patterns and they will be able to create this equation, but they won't be able to explain why this equation is the way it is. Why do we look at some specific parameters more than at other specific parameters? So this is really only going to be a problem where explaining how the conclusion was reached is an absolute must. For example, something like court cases, law. You can probably make a neural network that is going to be able to predict the guilty party and the innocent party, even by something as simple as looking at their faces. Ignoring the fact that this is going to be circumstantial evidence, let's ignore that for a second, that this isn't going to be accepted by most courts on that basis. You can probably create neural networks that are able to do something like DNA samples, predict based on DNA samples, are the DNA samples similar enough, or something weird like that, but they won't explain how that conclusion was reached. So on that basis, neural networks are going to be largely, the evidence produced by them is going to largely be inadmissible at courts. You can't just have a neural network say, okay, I looked at this person's face, I don't like their face, 50 years of jail, life sentence, death sentence, guilty, guilty, guilty. It's not going to happen. even though you can probably, like purely from a scientific perspective, you can probably get some sort of accuracy just by looking at a person's face. There's an entire science about this. You can predict a person's personality just by analyzing their face. Another example of where this isn't going to be used very often would be, for example, scientific research. You can't have you can't just write a scientific paper saying that the neural network predicts that for this sort of natural phenomenon, we will be able to predict it using this equation. But why is that equation the way it is? Like, we need to show some sort of derivation, explain some sort of logic behind it. Like when Albert Einstein came up with E equals mc squared. By the way, that is an amazing equation. Einstein actually derived that based on intuition. So you can predict it mathematically. Well, it was predicted mathematically, but based off of intuition, based off of sort of thought experiments of what would happen. And Albert Einstein proved that in many different ways. But you can't have a neural network that just comes up with this equation, E equals mc squared. And the entire scientific community worldwide would just be like, praise the mighty neural network. Not going to happen. So far we've talked about how neural networks, they're really amazing. They can do all of these different things for us automatically, how they can classify all of that data, find all of these correlations automatically on their own, and they're able to predict stuff on their own. Neural networks, if they were to do absolutely everything we have on their own, then we as developers would be out of work. So let's discuss a little bit as to what the developer's work actually looks like. So collecting and processing data. That is the first thing you need to do. If you want to make any kind of neural network for any kind of process, you will need to teach it. The neural network needs to read some data in order to find its correlations. Like once it's sort of born, it doesn't know anything, but you need a lot of data to teach it. A lot more data than you would for a human, than you would anticipate for giving like a human. Typically, a data set that has 10,000 examples is going to be a tiny data set. Like hundreds of thousands of examples or millions. We could easily have a data set like that. Sometimes you can find these data sets online. Sometimes you can scrape them together from all sorts of projects that maybe other people had, like leftovers. But a lot of the time, someone will actually need to go out there and collect all of this data, process it, filter it, label it. Like taking pictures of cats and dogs isn't good enough. You need to also give a label as to which picture represents a cat and which picture represents a dog. So the neural network is able to read that label later on and say, okay, that's what a cat looks like. So this process is very tedious. It's sort of where the meat of this whole project is. It's the biggest step in the entire project. Like 60 or 70% of any AI project might be just about collecting that data set. Then, after you've collected the data set, so data sets will be collected, like people would be hired specifically for this purpose. Like full-time, people would be employed full-time and their job will be to just help collect some specific data set. Then after that data set is collected, we will want to create an architecture. We would want to define some sort of architecture for the neural network. A neural network consists of neurons. Those neurons can be placed in any sort of order. There are many different types of neurons. So we can choose all of these combinations of parameters. And we want to choose some combination of parameters that works, that gives us good results for the data that we have. Then, after we've selected an architecture, once we see that it gives us good results, we will want to sort of observe the accuracy. Neural networks are very prone to a phenomenon that is called overfitting. Overfitting is when a neural network sort of memorizes the data that it's seen, but it hasn't been able to extract all of the useful information from that. So for example, something like a student preparing for a math exam. You can show that student all sorts of example problems, like how to solve this problem, how to solve that problem. But the questions on the actual exam will be different. The hypothesis here is the reason that the questions on the exam are different is because it's sort of anticipated that the student will encounter questions in real life that look sort of similar, but their exact sort of parameters are different. So for example, a student might remember that 7 times 5 equals 35. They don't actually know that 7 times 5 equals 35. Like, they can't perform that multiplication, but they remember that. So they would be able to tell you that 7 times 5 equals 35. But once you ask them something like what 7 times 6 is, they won't know. That's an example of overfitting. There are many different ways which we can use to sort of combat overfitting to make sure that it doesn't take place. There are all sorts of different methods that we go over in our main course in great detail. Then once we are happy with the accuracy, so once we're happy with the accuracy on the test set, we are going to have just a little file on our computer that is going to basically store the entire neural network. The neural network is going to essentially come up with the equation that we need to solve a problem. It's going to come up with some very long, very intricate equation. And the exact form of that equation is going to be saved in a file on our computer. And this equation, I mean, it's going to be like thousands and thousands of lines long. So it's going to be stored either on the hard drive somewhere or somewhere on the, like if we're working on the internet, then it would be stored in the cloud somewhere. We'll just have a little file. We want to actually apply that somewhere. We want to use it somewhere. So we would want to integrate the service into production. If we made a program that recognizes voice commands, for example, like OK Google, we would want to integrate that into a phone. This task is sometimes done like with small companies, with very small projects. This step is also often going to be done by the same person who developed the neural network. Most of the time, the people who collect the data are different people. That's not the same person as the person who creates the architecture, tests the neural network, and then, so that person may or may not be the one integrating the product, the neural network, into what we call production. Sometimes it's going to be the same person, but for most medium and large companies, that is also going to be handled by some sort of separate department. So with that, let's discuss a little bit of how neural networks actually work. How do they learn all of their information? How do they come up with this magical equation that is used to solve any problem that we might have? Neural networks consist of neurons. So neural networks, they were discovered, you could say, discovered by mathematicians in the 1950s. First, we had biologists who made a representation of what they thought a human brain looked like, how they thought a human brain works, but they were wrong. The mathematicians took this model before they even knew, I think it was before they knew that that model was wrong, and they converted it into digital format. And as we found, it works quite well for digital purposes, for our purposes. So neural networks consists of neurons. Neural networks consist of neurons. They have tons and tons of neurons scattered in all sorts of different places, and neurons, they take in data from other neurons and they feed data into even more neurons. So neurons are connected in some intricate fashion among each other. Each neuron classifies the truth of something, whether or not something exists. So for example, whenever you touch something that is cold, like a packet of ice, there is a neuron firing. that is responsible for the feeling of cold. If you just came back from a marathon and are just really tired, out of breath, there is a neuron that is responsible for feeling out of breath. There is a neuron that is responsible for feeling tired. If you see something like ice cream and you think, tasty, there is a neuron firing that says that that's ice cream. And there is another neuron that is activated that makes you want to actually eat that ice cream. So anything, any truth of any statement, anything that exists sort of in the given situation will be classified by a neuron. If a neuron doesn't fire, that means we don't have that feature. If a neuron does fire, that means we do have that feature. And by the way, the example I gave for humans, like feeling out of breath, touching something that's cold, in practice, that's done by millions, like clusters of millions and millions of neurons. Right now, I'm just sort of oversimplifying this for example's sake. So if we were to look at pictures of cats and dogs, we might have a neuron that sees like this nose here. And it's going to activate if it sees that nose. And if it activates, it sends some signal to even more neurons. We might have a neuron that sees the whole face of the cat, like the whole shape of the whole head. And if it sees that, it's going to send a signal onto other neurons. And if it doesn't see that, it's not going to do anything. So neural networks, they consist of tons and tons of these neurons. These neurons are going to be connected in some intricate fashion among each other. They will take in data from neurons, and they will feed that data into all sorts of other neurons. Neurons are just going to be represented by a numerical value. They will have some value in them. So we might have a neuron right here, and it's going to have the value of 0.5, or it might have the value of 1. So not only is a neuron going to determine if something exists, but it's going to determine how much it exists, sort of the extent of the truth of some statement. For example, you might have a neuron effectively asking something like, is the weight of some animal more than 5 kilograms? Well, you can have a weight of an animal be something like 4 kilograms, in which case that neuron is not going to activate. It's going to have a value of 0. Or you might have a state in which it sort of activates, where the weight of the animal is something like 5.1 kilograms, in which case it's going to activate, but it's going to activate sort of very, very weakly. Like, yes, the weight is more than 5 kilograms, but really not by much. Or you can have a weight of just 100 kilograms, in which case the neuron will have a value of a resounding 1, which is it's saying that, yes, absolutely, the weight is much, much more than 5 kilograms. So this sort of architecture, where we have neurons connected to other neurons, taking in data from yet more neurons, it's what we call a fully connected neural network. A fully connected neural network consists of layers. So all of these are layers. All of these columns that you see, they form a sort of layer. And each neuron in a column, in one of these layers, is connected to all of the neurons in the next layer. It feeds its data into all of the neurons in the next layer, and it takes inputs. It takes data. It retrieves information from all of the neurons in the previous layer. So for a very simple example, let's say that we have a task where we want to classify if some animal is a cat or a dog, given 3 parameters: its weight, its height, and its length. We would have 3 neurons responsible for the input data. 1 neuron that takes the weight of the animal, 1 neuron that takes the height of the animal, and 1 neuron that takes in the length of the animal. Then these neurons are connected to other neurons by these lines that you see here. They are called weights. So these weights connect all of these different neurons. And when this data is fed through a neural network, whatever input we have here, let's say we have a weight of 5 kilograms, it's going to be multiplied by this weight. Let's say it's a weight of 0.1. So we will have a value of 0.5 for this neuron. Then we would have a height of something like 1 centimeter. I don't know of any cat or dog that is only 1 centimeter tall. Let's say 10 centimeters at least. Maybe it's like a baby cat. And we are multiplying it by 1. So we have this 0.5 from here. We are going to be adding to this value 10 times its corresponding weight, which is 1. And then we will be adding in this length multiplied by its corresponding weight. And that is going to come up with the value of this neuron. This neuron is going to be responsible for classifying the truth of some other statement. It might ask something like, is the length of the animal at least double its height? Or it might ask something like, we might have this neuron asking something like, is the weight of the animal more than 5 or more than 10 kilograms? We might have this neuron asking something like, is the weight multiplied by the height, or is the weight plus the height, or is the length plus the height bigger than the weight, or something else like that. Then we will have neurons in our next layer. These neurons are going to be asking even more questions based on the combinations of all of these questions. They are going to be asking like even more weird, complicated questions, like, is the ratio of length to weight bigger than the ratio of length to height, or something like that. So these examples that I'm giving right now, hopefully they're not too removed from human logic. But in practice, the questions that the neural network will be asking will be really, really removed from human logic. Like, we will have no idea why the neural network asked the questions that it asked, but it did, and it works. Then finally, we have 2 neurons in the output layer. So this neuron is going to give the final result of what we actually have. In the case where we want to predict some category, like we have this animal, does it belong to the category of cats or does it belong to the category of dogs? We would have as many neurons in the final layer as our number of categories. Let's say that this neuron is responsible for the cat and this neuron is responsible for the dog. So these numbers will propagate throughout this whole neural network. They will be multiplied by different numbers, and we will have our final results. We might have the result of a cat being equal to 1 and the result of a dog being equal to 0. That means that the neural network thinks that whatever we fed it, whichever data we fed it, is going to be a cat. The animal that it saw the weight, height, and length of, that's going to be a cat. It doesn't think that this is like at all related to a dog. It thinks that there is a 0% chance of this being a dog. Conversely, we might have something like the value of cat being 1 and the value of dog being 2. This means that the neural network is a little bit unsure if the whatever parameters we gave it, if that corresponds to a cat or a dog. So it would say that it still thinks that this is more of a being, like it's more of a dog. It thinks that whatever data we gave it, it represents a dog more than it does a cat. So our final result will be dog. Then if we were to try to compare 3 categories, like we might have not just cat or dog, but we might have something like cat, dog, or beaver. So we would have a 3rd neuron here that is going to be responsible for the beaver, and its value might be something like 0.5, which means that the neural network does not think that this is a beaver. So folks, if you have any questions at all, I invite you to ask them. I understand that this step might be a little bit confusing, a little bit unintuitive. So if you have any questions whatsoever, I would be more than happy to answer them. So that is how a neural network classifies all of its information. But the neural network, it's not going to know anything when it's first created. So let's talk about how it actually learns. Let's talk about the sort of the math or how it's going to learn using math, which once again, we won't be delving too deeply into math. I know that a lot of people get stressed out when they hear the word math. So one thing I want to mention right away that I probably should have mentioned earlier, we have frameworks which contain all of the math and all of the code that we need for us. So we only really need to know the minimum amount of math. Right now, this is just going to be a very general, rough description of the theory. We are going to have two data sets that the neural network is going to train on. We have one data set that the neural network is going to train on, actually. And that is called the training data set. It's going to contain a long, long list of examples. In this example, it's going to contain various parameters like the weight, the height, and the length of that animal, and it's going to say what that animal actually was. Like, was it a cat or was it a dog or whatever it was. And we will have many, many different examples. Here we have 20,000 examples. 20,000 examples is not even a large neural network. That is like a small neural network that we can only really use for a simple task. So the neural network is going to try to predict which animal this corresponds to whenever it sees these examples. Given some weight, some length, and some height, it's going to try to predict if that was a cat or a dog. It might read in these parameters and say that this corresponds to a dog. But then it's going to look at the label and it's going to see that it was wrong. That animal wasn't a dog, it was a cat. And this is when the neural network will perform what is called backpropagation. It's going to perform an algorithm through which it changes all of its weights. These are, so the weights, to recap, the weights, it's going to change the values of all of these connecting lines in such a way that whenever it sees that same data again, it's going to predict something closer to the actual answer. So whenever it sees this data again, hopefully it's going to predict that this is a cat and not a dog. If it predicted correctly, if it made the correct prediction the first time around, it's not going to do anything. It's going to leave everything as it is. But whenever it predicted something and it saw that its prediction was wrong, it's going to change all of the weights in such a fashion that the final result will be closer to the correct answer. And it will iterate through all of these 20,000 different examples. It will iterate through all 20,000 examples. And then it's going to jump to what is called a new epoch. That is when it tries to predict the same 20,000 examples again. And we can specify the number of epochs. Typically, we will have at least a few dozen epochs. So the neural network is going to read all of this data many, many times, and it's going to try to predict every single example. And hopefully it will have learned by then. It will have learned not to just memorize all of these numbers, but it will have learned all of the correct sort of things that it needs to look for, all of the general tendencies. By setting its weights accordingly, it is able to make its neurons ask the right questions. So when we first initialize the neural network is going to be asking pure garbage questions, like questions that don't make any sense. Is the weight of the animal bigger than 50,000 megatons? That doesn't mean anything. Every animal weighs less than 50,000 megatons. But once it learns over many, many different examples, it sets all of its weights, it gradually changes all of its weights in such a fashion that the questions that the neurons are asking are reasonable. At that point, the neuron might ask something more reasonable, like is the weight of the animal more than 10 kilograms or something like that. And then after we're done this, we will want to actually test our neural network on examples that it has never seen during the training process. That is what we have, what is called the test data set. So we need to make sure that the neural network hasn't just memorized all of the examples that we showed it. That is a phenomenon. Overfitting happens a lot. The only way to really test and make sure that we don't have any sort of overfitting is to give it another data set and try to see how well it performs on that data set, that it's all of that data that it's never ever seen before. So we would ask the neural network to try to predict every single example in the test data set, and then we will have a final percentage, like how accurate the neural network is. And at that point, if the accuracy is good enough, we will say that we're happy, we want to use this neural network, or maybe we want to train it a little bit more to get even better accuracy. Or if it's horrible, if it's just the accuracy is absolutely horrible, then we would need to go back and sort of change up the entire architecture. So whenever we change the architecture, we will make a bunch of hypotheses. We will say, okay, what happens if I add these neurons over here? Or what happens when I remove those neurons? And that work really resembles, it's really more of a, like testing hypotheses. It's more of actual, reminiscent of actual scientific work than the vanilla programming that we often think about. And we'll be talking a little bit more about that as well. So the entire process of learning is all about just adjusting the weights. The only thing that changes during the learning process is the neural network just readjusting all of its weights. It doesn't change the number of neurons. It doesn't change any other parameters like the type of neurons that we have or any of that. So the neural network contains some architecture that specifies that we have all of these neurons that feed into all of these other neurons. It contains how many neurons we have. It contains what the types of those neurons are and how they're connected. And it has the weights connecting those neurons. These weights are changed by the neural network. They are initialized randomly, and they are changed during the learning process. So we have a dense architecture. We call this a dense architecture whenever we have a fully connected architecture, and numbers just propagate down this architecture. So they would propagate, and then we would have our final results. We would have some number contained in the actual neuron that is going to be multiplied by this connecting weight. And then we would have some other value here that will be multiplied by this connecting weight, and some other value here multiplied by this connecting weight. And we are going to add all of those weighted sums to get some value. And typically we will also want to add a bias on top of this. A bias is just a static number like +5 or -2. We would want to add or subtract something. And that's going to be initialized randomly as well. Then, whenever the neural network tries to learn, so it's going to do this through a process that is called gradient descent. Gradient descent is going to try to reduce the overall amount of error contained in the neural network. The measurement of the error is sort of a numerical measurement of how wrong the final result was. So if we were off, like if we were try to predict the stock price tomorrow or something like that, try to predict the stock market tomorrow. If we are only off by 1 point, like we would say that the Dow Jones index is going to open at 26,001 point, and it opened at 26,000 points, so we're off by 1 point. That prediction is not as incorrect as if we were off by 5,000 points. Like 5,000 points is really, really terrible. Like we predicted 31,000 and the actual result is 26,000. That is absolutely terrible. Whereas 26,001 is almost exact. It's a wonderful result. Or something like predicting the weather. If we predict that it's going to be just an absolute heat wave tomorrow, and it turns out that it's actually a blizzard, that's not as bad as predicting that it's a heat wave, but just being off by 1% humidity point, or being 1% off by just 1 degree. So error is a sort of numerical measurement of how wrong the result that was predicted by the neural network was. When we have a high error value, that means that the neural network is completely wrong. And when we have a low error value, that means that it's almost spot on. It will typically never be exactly spot on. We will just get it to be very, very close to the exact answer. So we can define the loss function however we want. Error is also sometimes referred to as loss. We can define that function however we want. It's up to us depending on which specific case we're looking at. We might want to define something like the loss can be by however many points we were off. So if we were off by 5 points, the loss is going to be 5. Whereas if we were off by 5,000 points, then the loss would be 5,000. We can define it as that value squared. So if we were off by 5 points, 5 squared is 25. If we were off by 5,000 points, 5,000 squared is 25 million. We can define it in any way we like. But ideally, it's going to be a numerical representation of how wrong the result was. So when the neural network predicts something and it sees that its result was wrong, it's going to try to decrease that error. And the way it's going to do this, it's going to change all of its weights. It's going to essentially take a little step. So if we had only one neuron in our neural network, which is an extremely simple neural network, we would have this sort of two-dimensional graph, this sort of line graph. But for real examples, we would have like a million weights is not even a large neural network. So we would have a million dimensions and we obviously can't represent that. So this is sort of a very simplified representation. But for however many dimensions we would have, we would know exactly where we are, exactly how much error we have, and we would know which direction we need to take a step in to reduce that error. So here we would know that if we go in this direction, we would reduce the overall error. And if we go in the opposite direction, we increase the error. I'm going to say loss because I can't seem to say error. So we are going to take just little hops each and every time the neural network changes its weights until ideally we get to some minimum value. Ideally, we would want to get to the absolute global minimum. In practice, actually, we wouldn't want to go here. Just in theory, we do want to go here, but in practice, this is where the neural network tends to overfit a little bit. So we'll be happy with some area like this. That is the goal, to reach this area by taking these little hops. Once it takes its first hop, it does the exact same process again. So it sees that the error is located over here, the loss is located over here, and it knows that it still needs to head in this direction to decrease the loss. So it takes another step in this direction, performs the same algorithm again, sees that it needs to keep heading in this direction, heads in that direction. We want to make sure here that the neural network isn't taking steps that are way too large. You might be tempted to think that we could just do one big step here, but we can't actually do that because we don't know what the actual step size we need is. If we were to select a step size that is way too large, we would just hop all the way over to the opposite end, then perform this exact same calculation here, see that we need to head back in the direction that we came from, and that's when we would take another big, massive leap back, and this would lead to nothing. We would just keep jumping back and forth, taking bigger and bigger steps. We don't want that. If we select a step size that is way too small, we would just be taking tiny, tiny little hops. And then we would reach this local minimum. And that's when the algorithm is going to say, okay, now we need to head back in the opposite direction to reach this value, this smaller value of loss. So we will keep heading back and forth in these tiny, tiny little steps, and that is also absolutely no good. So we want to select a step size that is going to be large enough to overshoot this initial barrier. And that's going to allow us to keep going and going up until wherever we're happy with, but one that doesn't sort of have us just leap back and forth in massive steps and also not make any progress. In practice, a lot of this headache is going to be alleviated through something that is called an optimizer. An optimizer works on some very complicated, intricate math. Once again, we won't need to know any of that math because it's predefined for us in the frameworks and in the libraries that we'll be using. The optimizer is going to try to see if we're consistently taking steps that are way too large. It's going to try to reduce the step size. So the step size does not have to be constant. It's going to reduce the step size until we hit some area that we're happy with. So it's going to do something like this. If it sees that the step size is too small, like we're getting stuck in this local valley and we just can't breach it, we just keep bouncing back and forth, that is when we would want to increase the step size. So we would increase the step size by just enough so we can overshoot this valley and continue with our progress. So the math involved in that is quite intricate, and we really don't need to know it. Like if you want to create your own optimizer, that's more of a senior developer job, then you probably would want that. But for most users, for most developers, there is no need to know every single step inside that algorithm. Do you ever find multiple local minima? How do you manage if there are significantly different weights associated with those local minima? Most of the time you will have many, many local minima. So the neural network is going to keep training and it's going to keep changing all of its weights after every single example. And it's just going to reach a new minimum. So if you have multiple local minima, you would want to overshoot the minima that aren't very good. Like you would want to overshoot this minimum, and you would want to just keep making progress until you reach a local minimum that is reasonably small. How do you manage if there are significantly different weights associated with those local minimums? So once again, you would just select whichever weights. You would see which weights perform best on the test data set. So you would sort of see which weights give you the best results, which combination of weights gives you the best results for whichever task you want to do, and you would select those weights. So also, good question. Thank you. Okay, with that, let's view, we went over so much theory right now, let's view a live demonstration. Let's take a little sneak peek at what these neural networks actually look like. This is Google Colaboratory. This is a coding environment that we can use sort of in the cloud that Google offers us for free. So Google Colaboratory, we will be using it in our main course because Google allocates a free GPU for us. It actually gives us quite a powerful GPU to play around with. Like buying something like that will cost probably between $500 and $1,000, very roughly. But Google Colaboratory allocates this to us for free. So this is what this coding environment looks like. We don't need to download Python. All you really need is a Google account. Our university made several examples of simple neural networks just for demonstration purposes. So right now I have to log into my Google account to let Colaboratory access my Google Drive to retrieve all of that information. If you have any questions in the meantime, while all of this code will be starting up, I will be absolutely happy to answer it. So this is what the code looks like. In our case, all of the code is sort of already made for us. We're just using the libraries that were made by our university. These are just some very simple neural networks that we made ahead of time. In practice, the code is going to be a little bit more sort of complicated, but not really. Like nowadays, the code is very, very simple. When we use TensorFlow, when we use Keras, these are the main libraries and frameworks that we'll be using. Coding is also going to be very, very easy. Like 15 years ago, back when this whole thing was starting, people needed to know all of the math. They needed to know how to code very, very well to create all of these neural networks. Nowadays, this job is trivial. Like, without any exaggeration, middle schoolers are able to do this. So our first neural network is going to show examples of cats and dogs. So these are what different cats look like, just pictures of various cats. And then we have like some dogs mixed in here. We want this neural network to actually predict what is a cat and what is a dog. Like, we want it to say, okay, this is a cat and this is a cat, that this is a dog, or these are dogs, and so on. So let's train our model. This is a very simple model. That's why it trains very, very quickly. In practice, it would take, like, for a simple task like this, it would take a little bit longer, but not too much longer. For the really high-end beefy neural networks, those take a long time to train. So we have epochs. An epoch is how long it takes, or it's when the neural network processes every single training example. And then it moves on to view those same examples and try to predict those same examples again and again and again. We have two parameters that we need to look at. We have the accuracy on the training set. So this is how accurate the neural network was with the examples that it's previously seen before. If you look closely, you will see that this tends to go to 100% very, very quickly. So very often the neural network is going to be amazing, just amazing at predicting every single example that it's seen before. But for the test set, so these are the examples that it hasn't explicitly seen before, we want it to generalize. The accuracy is usually going to be a little bit smaller. So 50% followed by 58%. Then as we train it more and more, this keeps going up until we reach like 92%. And then it sort of asymptotes. It reaches 93%. If we were to train it a little bit more, we could maybe squeeze out 94, 95%. But it's not going to go any farther than that. There will be a sort of a soft limit that we will reach, and we won't really be able to go through that without either changing the architecture of the neural network or changing the data set that it's learning on. So if we plot out the accuracies on the training set and on the test set, we can see that the training set was always more accurate. So for each epoch. So now let's visualize these results. The neural network, once it's initialized, it doesn't know heads from tails. It's horrible. It just groups everything and says that it's the exact same animal. But once it's trains and once it sees that whatever predictions it's made are wrong and it tries to make better predictions, that's when it starts to recognize the difference between these animals. Okay, something weird is happening with Colaboratory. Hopefully it's not going to keep blinking away all of this demonstration, but it's going to predict that these are different animals. It's going to start to learn that all of these are different animals. And it's going to start to, so the distance between them represents the neural network seeing that they are more different, sort of. In our example, so we have a 93% accuracy. These animals, all of them are classified correctly. But clearly the accuracy isn't 100%. So if we were to visualize more examples, maybe we would have some cat that maybe looks slightly like a dog or something, and it would be classified over here. Like, the neural network isn't quite sure about that. But if we have better neural networks or better data sets, those problems go away. Next, let's try to predict a regression problem. So far, we've seen a lot of what are called classification problems. Classification problems, does this thing belong to category A or category B? Regression problems is when we want to predict some exact value, like we want to predict what the stock market is going to be like tomorrow, exactly what the opening price is going to be. Or we might want to predict something like exactly what is the weather going to be. We might have some sort of weird mathematical sort of prediction, like something physics-based, like something astronomy-based. If some meteor passes through all of these celestial objects, it picks up energy due to gravity. What speed is it going to have? Something like that is a regression problem where we have one specific value in the end, and we want to predict that value. So in our case, we are going to be predicting car prices. We have a database that contains information about all sorts of different cars, contains their manufacturer, the model, so Silverado 2500 HD, the year it was produced, in the mileage. And then we have like the fuel, is it a diesel or a gasoline car? We have the body of the car and the KPP. By the way, I don't know what these things actually are. And the great thing is that I don't need to know what the KPP and what the body actually are, what these parameters actually are, because the neural network will learn how much they affect the final price on its own. So the goal of this neural network is to predict what price we can sell that car at. When we train this model, we won't have accuracy anymore. We will just have a single parameter that is responsible for our loss. And over time, this loss is going to decrease more and more and more and more until we hit a number that is reasonably small. So the loss is a measurement of how wrong we were. And finally, we can see the visual representation of this in every epoch. So when we start out, the neural network, okay, sadly, we don't get to see epoch 0. So we get to see the epoch number over here, and we get to see the accuracy in each epoch. Epoch 5, it's all over the place. The actual prices don't really correspond very closely to the predicted prices. We want them to correspond exactly. But the more we train that neural network, the closer and closer these results actually are. For our next demonstration, this neural network is going to try to analyze voice commands. So it tries to interpret the meaning of voice commands. So one question was, which was a wonderful question, by the way, is this an example of a deep neural network or a simple neural network? So what I'm going to be showing right here is closer to an example of a simple neural network. We can make deep neural networks that are way more intelligent than this. But for now, this is going to be a simple neural network. So let's import this module. We will have many different audio samples. We will just have audio samples containing the words like air conditioner, or lights, or TV, and then we'll just have some background noise, like people talking in the background, people chatting, TV, like the television actually playing, people in the TV saying something, or the radio. The idea behind this neural network is to get the neural network to sort of know what you want it to do. So we have this big project that is called a smart home. That is when all of the devices inside the home are intelligent. They understand what their user actually wants them to do. So instead of manually flipping the switch to turn on the lights or to turn on the television, instead of grabbing your remote and manually pushing the button, you could just say TV turn on or lights off. So you might have seen something like this a lot with Alexa. Right now, we want to train a neural network that is going to be able to predict the actual voice command and its meaning. Whenever a computer sees some voice command, really all it sees is, like if we were to plot this out, it sees just some voice command that looks like this. It just sees the audio wave, right? And somehow it has to recognize that this corresponds to the word air conditioner. So we have spectrograms. Spectrograms are they're a 2D pictorial representation of the actual sound wave. It's taking basically samples in different time windows, and it's saying how much amplitude different audio waves have in each frequency. So a word air conditioner, like here I recorded myself saying air conditioner, that looks like this. The word lights looks like this, and the word TV looks like this. Then we have a bunch of background noise. Something that sounds like this. That's just something that looks like that. So for the purposes of training this neural network, we needed we got away with a small database. Ideally, we would need a larger database. So I just recorded myself saying all of these words and recorded some background noise. So let's train our model. By the way, if none of that made any sense, what I said in the actual audio recording, that's because it was just a random text generator. Right away, we have a neural network that is training. It is giving us the accuracy. It's almost reached 100% accuracy very quickly on the test set. But once again, the accuracy on the training set reached 100% very quickly. But the accuracy on the test set lags behind. It's hovering like 90, 92, 93%, and then it reaches 94%. A lot of the time, whenever a neural network is training, usually it has a tendency to increase its accuracy over the epoch, but sometimes it does something like it starts increasing the accuracy and then it can go down in accuracy. That can happen a lot, and especially with more complicated neural networks, like the actual pattern looks something like this. Like there is a general tendency to have better results, but sometimes it can train and it will essentially know less after it's trained in that one epoch than before it's trained. So now we are going to look at the results. Let's look at, okay, this is taking a while to load. So we have some recording, and somewhere in this recording, there is the word air conditioner. That is essentially me telling the neural network to, well, right now the neural network isn't going to do anything because this is just a test, but hypothetically, this would be me telling the neural network to turn on the air conditioner. Background noise. Let me turn the voice down. Hopefully that's not too loud. Then somewhere in the middle, we have the word air conditioner. There we go. So there is a bunch of background noise, and somewhere in that, there is the word air conditioner. And when the computer reads the whole spectrogram, it's going to analyze. It's going to look at it bit by bit. It's going to ask, is this related to the word air conditioner? Or is this related? Is this? And so on, until it finally sees the part of the audio wave that actually corresponds to the word we're looking for. So it's highlighted this part. Then it's going to highlight that part and we can see it right here. The audio clips aren't playing at all. Let me try to fix that very quickly, if I can fix it. Yikes. I don't think I can fix it. Yeah, really sorry about that. Maybe if I can. Do you hear that at all? So we have audio that sounds like that. And then that's just the part that it selected. Okay, I honestly don't know if that worked. Please tell me if you heard anything there because I'm just playing around with the audio settings live here. I don't want to mess anything up. If you didn't hear it, basically we just have audio clips that contain just a bunch of background noise. That's just me talking. And at one point, somewhere in that background noise, I say the command that I want the hypothetical smart home to do. So that might be something like the word lights. It's going to select this part. It's going to explicitly select this part, and it's going to say, okay, this audio wave corresponds to the word lights. It's going to say, I saw this. The audio, okay, wait. No sound came out. Yeah, I tried to switch like microphones. Yeah, I'm really sorry. I can't fix this on the spot. Like I tried to switch microphones or like switch the speakers, sort of the input for the audio, and I hoped that might do something. Yeah, I'm really sorry. We will have more examples of this in the next presentation, and we'll be absolutely sure to fix it by then. So then we have the word TV. The actual spectrogram looks like this. And it selects this part of the audio wave. And it says that this part corresponds to the word TV. So yeah, apparently you can't hear what is playing on my computer, which sucks. I'm sorry. Share computer sound. There we go. Oh my goodness. Very sorry, child. Sitting so totally forbade 100. Is that better? Is that any better? There we go. Yes, thank you. Yo, thank you for letting me know. Air conditioner. Air really conditioner. So this is what all of the audio sounds like. Instrument cultivated alteration, any favorable expression. We have all of this audio, and somewhere in this audio clip, I'm going to say the word lights. And from mean light year lights. There we go. And from, so the neural network has highlighted this. It says that this corresponds to that audio. That part, that word that I said, that is the word lights. Okay, let's get back to our main presentation. So we offer 2 courses that can teach you everything about data science and neural networks. They are very comprehensive courses. The courses, we have 2 streams. We have the light stream and the pro stream. The light stream is oriented for people who have never programmed before or have programmed very little. So a lot of people come to us from all sorts of walks of life. People that come to us from the medical sector, from banking, from all sorts of sciences that aren't necessarily related to neural networks or computers, like physicists, for example, or engineers even. We have people who are fresh out of high school, people who have been just working as grocery clerks, all sorts of works of life. And we teach all of these people. So by the end of our main course, you will be pretty comfortable with all kinds of neural networks that we have, with regression examples, with text classification. You will be comfortable with the deep neural networks that we have, with generative neural networks. It's a very comprehensive course. So it takes 6 or 9 months depending on the stream. For the light stream, in fact, for all streams, we guarantee that by the end of the course, you will be able to find a job. You will be able to become employed as a junior AI developer. Like this part will actually be written out in our contract. We have our own domain, which we use to sort of network with the big companies that hire all the different AI developers. They know who we are. They know that we are a big commercial university. They know that we train people to a high standard, and they like to hire our graduates. So by the end of the course, you will know all of these things. You will complete your own thesis project that you will be able to add to your own resume, and you will have all of these skills, and we will give you all of the support you need to find employment in the industry. AI development is a wonderful industry. I'm going to be a little bit elitist, and I'm going to say that it's better than every other kind of developer job out there. AI developers, AI is just such a new and it's such a big industry. Artificial intelligence is used everywhere, and it's going to be used everywhere. It can be applied everywhere. Right now, we have the technology to apply it in virtually every single industry, in every field, and in almost every single job. Even if it's not to directly replace people, like replace the human element, we might help actual people in some ways using AI. So there is going to be a lot of demand in the future for this. That is why the wages that AI developers receive, they're a little bit higher than what people who develop video games or like web developers receive. For entry-level developers in the United States, wages usually hover from around $45,000 to $85,000 a year. 85,000 being something more like Silicon Valley, New York. 45,000 is more for the small towns out there, or maybe even remote work from rural areas somewhere. So we absolutely guarantee employment. Like, once again, it will be written out in our contract. So far, we've been able to find employment for every single graduate that we've had. Like, we've never had a situation where we haven't been able to find someone that is going to hire this person. We handle all of the hassle in terms of seeking employment through our own domain. All you need to do really is to just show up for the interviews. So it's only a matter of time. Everyone will find employment. Like, if you have some specific criteria, like you only want to work remote and you only want to work in this very, very specific industry, remote isn't going to be an issue. Right now, everyone's working remote. If you only want like employment in this very, very specific narrow field, like you only want to work with spaceships, something like that, then it will take a little bit longer. But in general, it takes around 2 months on average to find employment. So for people who have some prior experience programming and you want to become an AI developer, like maybe you were a web developer before, or maybe you were a game developer before. There are some people who come to us who are like that. Or maybe you haven't ever had an actual job in the industry, but you've sort of taught yourself how to program in any language. For people like this, we recommend the Pro Stream. The Pro Stream is more geared towards people who have the sort of programmer's mindset. You don't exactly need to know the actual code, the language. Python is the simplest programming language out there. Like, it takes, if you already know how to program, learning how to program neural networks in Python will take like a few days, maybe not even that. The code itself is very simple. So this is more geared for people who just sort of have the programmer's mindset. These people, usually once they finish our courses, they are able to find employment that is a little bit above the entry level, sort of the entry level jobs. So they are able to make somewhere between 60 and 120K a year. And there are also some people that, so we're a commercial university, we teach people, but we also make neural networks for governments, for private businesses. We make neural networks for case-specific purposes. Sometimes we do a little bit of both. Sometimes a company might send us their developers, sort of like ask them to, like they would ask us to teach that person how to create this neural network, and we would help them create neural networks. We would teach them to create neural networks in general, and we would also be helping them from day one to create the neural network that they need for the specific purpose of that business. So no one fails our courses, by the way. because we offer help. We offer as much help as is needed, basically, until you know all of the material, until you can actually complete the thesis statement and graduate. We help you at every step of the way for as long as is required. So our 2 streams for the main course, the pro stream takes roughly 6 months to complete. For both streams, there is 1 lecture and 1 new topic that we will be covering every single week. Like 1 week, we might be covering regression neural networks. The other week, the next week, we might be covering image classification, convolution, and after that, we might be covering time series. In the pro stream, we have 26 lectures in total, and roughly speaking, that takes about 6 months to complete. You'll have to dedicate about 10 hours a week for each topic. So that includes viewing the lecture, completing all of the homework. There will be homework at the end of every single lesson. And then we'll have people that analyze that homework for you and give feedback. And then you will also want to probably fix any mistakes that you made. The light stream consists of 39 lectures. And the light stream consists, so it takes about 9 months to complete the light stream. All of the content that the pro stream and the light stream cover are the exact same in terms of neural networks. The light stream has an extra 13 lectures that go before we delve into neural networks. So we start with the very, very basics, like learning how to program in Python. Then we go over some of the frameworks that we're using. We will touch a little bit on data science in general and a little bit on the math. Like it's nothing really complicated. It's like a review of high school and a little bit of first-year university math. Just a few topics from first-year university that really aren't very complicated. And then after the 13th lecture, you will delve into neural networks, same as the pro stream. So if you feel confident that you know how to program, you can select the pro stream. You will finish faster. 6 months versus 9 months, you'll be able to find employment sooner. If you're not feeling sure, we strongly recommend the light stream. Both courses, both streams start on the 26th of September. So the pro stream lasts 6 months, the light stream lasts 9 months. And once again, I want to highlight that job placement is absolutely guaranteed at the end of this. We have never had anyone that hasn't been able to find a job. We will specify explicitly in the contract that we will use our own domain, all of our clients, to help you find employment until you actually find employment. It's just a matter of time. We have a team of TAs that are dedicated to answering any questions that you might have about any topic around the clock. Like, I'm not kidding, 24/7 for the entire duration of the course. We will be checking homework and we will be happy to discuss anything that we went over in the course, any theory questions. If you're having trouble with some specific problem or something in general, we will give you as much help as is needed. We are available around the clock. We will always have someone 24/7, and that is not an exaggeration. So if it's like for anyone connecting from every part of the world, for everyone connecting from every part of the world, so if it's maybe daytime for you when it's nighttime everywhere else, you can ask us, no problem. So you can either like text us using Slack, WhatsApp, or Skype, or whichever service is more convenient for you, or you can book a video chat with us. All of the learning is going to happen remotely. So everything is going to be remote. All of the homework is going to be remote. Checking the homework, evaluating all of that is going to be remote. The thesis project is going to be remote. You can add the thesis project on your resume, by the way. We will also give feedback as to how to make your resume, how to make it look nice. So that is going to be remote as well. The final exam, we will have an oral exam at the end of the course. That is going to be remote. We are going to have So the thesis project, testing your thesis project, giving feedback, that is going to be remote. And at the end of that, we will also hand out a certificate that says that you've completed our course. We can mail it to you or we can send it by courier, whichever is more convenient for you. So in terms of pricing, both the light and the pro courses cost $3,490. With that comes TA assistance for the entire duration of the course. So however long the course is, you will have TA assistance around the clock 24/7 for the entire duration. That will come with 39 lessons for the light stream and 26 lessons for the pro stream for neural networks, and that comes with a guarantee of job placement at the end of that. Once again, it's just a matter of time. We offer internships that you can add onto your resume and make it look nice, even nicer. So internships, they last about 3 months, and they're also like really part-time, like 10 hours a week, I believe. Unfortunately, they're not paid as of right now, but we will be looking to make them paid internships in the future. And we also hand out a certificate. Like some of the big companies that actually hire people actually look at those certificates. For payments that are made, okay, it says the 6th of August. That's wrong. It's probably like the 14th of August or something. So for payments that are made within, you'll have to specify, but I think it's like about a week. We offer 2 gift courses on top of this. We have the Introduction to AI course. Introduction to AI course. So there are 7 more lectures in this course. It's a very chill, relaxed course where we just sort of talk about the theory. Like we talk about neural networks in general, where we can apply them, how different businesses, corporations of different sizes go about creating them, what sorts of people they hire. We cover very fun stuff like we talk about the hardware specs, where we can acquire that hardware, if we can rent servers on the cloud. There are 7 lectures. It's a very chill course. Like each lecture is like 30 to 60 minutes, and there is no homework at the end of each course. So it's just sort of a fun, neat little course. And this one, the Basics of Python course, it's another gift course that contains the first 7 lectures from our main course, from the light stream. The Basics to Python course, I strongly recommend everyone to take it, especially if you're not really sure, especially if you want to take the pro stream, by the way, and you're not really sure about some things. So the first 7 lectures that we cover, that we go over in the Basics of Python course, we go over some of the frameworks that we use a lot, some of the libraries that are very commonly used. We go over their theories, especially if you haven't used those frameworks very often, those libraries like NumPy, Pandas. We will teach you, so this course will teach you a lot of the theory about that stuff. And when you get to the main course, it's the difference. So the difference between knowing all about these frameworks, exactly their theory, what kind of functions they contain, is the difference of searching for 5 hours of how you want to do something, do one little thing, and not knowing exactly what you want to do, how you want to go about doing this, versus knowing that exactly this library contains this exact function that does something that roughly looks like this, and you only want to look up the exact syntax online in 30 seconds. Like, in my personal experience, this is from my personal experience, by the way, when I came to this university, when I took all of these courses, I knew how to program. I had like about 2 years of programming experience before then. I even had some experience with those particular libraries, but we go much more deeply into those libraries, and it saved me a ton of stress in the main course. Are there options that can be made after we are hired? For all sorts of payment-related options, I'm going to refer you to our sales manager. I don't know the exact ins and outs of that, to be honest. So you can contact them however is more convenient for you, by phone, by WhatsApp, by email, or you can visit the website. It's very easy to contact them on the website. You will have to ask them about that. So the Basics of Python course, strongly, strongly recommend, especially for the pro stream. If you feel that you're a good programmer, that you don't need to go over all of the material that we go over in the light course, you will want to have at least the first 5 or 6 lectures from this basics, from this introductory course. And if you want to take the light stream, you can sort of get a head start by sort of viewing all of the lectures that we have in the basics course and viewing all of the problems that we have. That will give you a head start before the 26th of September. Okay, that concludes our presentation. So if anyone has any questions whatsoever, I mean, there isn't any guarantee that I can answer them, especially if they're organizational questions, but I will try my very best. If you have any theory-related questions, I will be more than happy to answer that as well. Screenshot details on the screen. I'm sorry, I don't exactly understand. What do you mean screenshot details? Screen cap, yeah, of course. You can save them, absolutely. Yeah. So all of these contacts, absolutely. The contact information that was sent, yeah, you can screenshot that. That's our contacts. We want to be contacted. So absolutely, no problem. So if anyone has any other questions, theory or organizational questions, I'll probably be able to answer any theory questions. In terms of organizational questions, I may or may not be able to, but I'll try. So I guess if there aren't any questions, so we will be wrapping up this webinar. Everyone, thank you so much for coming, and I really hope to see everyone in our main course. So I'm just going to wait for just like a minute more in case anyone has any questions whatsoever. I will be absolutely happy to answer them. Okay, I guess everyone's happy. We have some questions. Can you show the contact info again very quick? Absolutely. You know what I can try to do actually? If Zoom lets me. There we go. You can see this, right, on the screen. The Zoom interface is glitching out for me. Why? Okay, there we go. That's better. So I'm just going to copy paste all of this information. Absolutely, feel free to contact us at any time regarding any questions that you might have. So I guess that concludes our presentation. I hope to see everyone in our main course. Take care, everyone. Take care, guys.